Ladies and gentlemen, please welcome NVIDIA founder and CEO Jensen Huang. 各位来宾，请欢迎 NVIDIA 创办人与 CEO 黄仁勋先生。
Hello, GTC Taiwan, 大家好。GTC is for developers and researchers whose work are so computationally demanding, you need the amazing power of the CUDA GPU to do your groundbreaking work. We have a lot to talk about today, so let's get started. We are at the beginning of a new day. We're at the beginning of a new day. Over the last 30 years, so much has happened to the computer industry. The PC revolution put a computer in every home and every desk. The mobile revolution put the internet in our pocket. The cloud computing revolution that we're experiencing now has given everyone a supercomputer and has turned computing into a service. And now, we're at the beginning of the AI revolution. This amazing new technology that's making it possible for software to write software by itself, for computers to learn, for machines to be infused with intelligence. In no technology revolution before this has the buzz and the energy around the industry been so great. This is the beginning of the AI revolution. And we are going to be right in the middle of it today. There are two fundamental forces that are the governing principles of this new computing revolution. These two governing principles, if you will, one starts from software, the other one starts from computing. Software has been fundamentally changed as a result of a new computing model called deep learning. This amazing new approach, where the software could detect and learn intricate features all by itself from a large amount of data. And from those features, hierarchically create and learn knowledge. It has the ability to study volumes and volumes of data, and from it, distill information. From it, recognize patterns. From it, generalize knowledge. Make predictions. Make observations. And as a result, for the computer to develop intelligence. Deep learning has already achieved amazing results. However, deep learning has one enormous handicap. It requires an enormous amount of computation in order to learn the necessary information from the data that is presented. And this is happening at exactly the same time that Moore's law is stalled. CPU performance is no longer scaling like it used to. Whereas the number of transistors continue to scale with the advances of semiconductor technology, microprocessor designers are no longer able to translate those transistors into more performance. We no longer know how to extract more instruction-level parallelism. As a result, the CPU performance has started to taper at exactly the time when we need more computational capability. The growing gap between the needs of computing and the capability of microprocessors has created the conditions, the perfect conditions, for a new computing model. And that new computing model is GPU computing. This computing model that we pioneered almost 15 years ago that we started to work on about 15 years ago and introduced 12 years ago called CUDA has really revolutionized computing. The computing model at its core is relatively simple. To create a processor that augments and collaborates with the microprocessor, the CPU, and does for the CPU what the CPU doesn't do well. The CPU is incredibly good at single-threaded operations. It's incredibly good at low-latency computing. Anybody can write software that will compile to a CPU, and the CPU will do a relatively good job. That is the strength of the CPU. It has democratized computing. It made it possible for almost anyone to learn how to develop C programs. However, the nature of the CPU prevents it from doing a very good job when the amount of data throughput is very high, when the parallel computing requirement is extremely high. And so we created a parallel special domain accelerator that works in conjunction with the CPU. Whereas the CPU is good for low latency computing, the GPU, the CUDA GPU, is extremely good for high throughput computing. And so in combination, these two processors in combination works together to turn that computer, bless you, to turn the computer into a computer that does incredibly well with single-threaded control code as well as high-throughput big data code. It becomes a computer that is good at everything. CUDA has really revolutionized computing as we know. And as a result, sped up applications and continue to extend the capabilities that are presented to us by the number of transistors. The more transistors that we're presented with, the more powerful of a computer we can create. And as a result, people are starting to see that CUDA GPUs is the path forward. It is how we can extend the post-Moore's Law era. Well, the adoption of GPUs has really grown tremendously over the last several years. In just the last 5 years, GTC attendees has grown by a factor of 10. 22,000 attendees this year. 22,000 attendees this year. There are 645,000 GPU developers in the world now. And in the last 5 years, the number of CUDA downloads has exceeded 6 million downloads, and almost 2 million just this 1 year alone. 1.8 million in just 1 year alone. So as you could see, the adoption of CUDA GPU programming is growing exponentially. Well, it's not easy to create a new computing platform. It doesn't come along very often. In fact, if you look at the history of time, and you look at what developers develop to and program to, the number of computing platforms they program to is actually very, very few. The new computing models come along very, very rarely. And the reason for that is this. It's both a chicken and the egg problem. You need a computing platform that delivers great productivity and great performance in order to inspire you. It solves a problem that you didn't have a solution for before. But if you develop that software, you need to know that the reach of that platform is so great that you can reach all of your customers. That the investment that you make in that software will be rewarded by the reach of the platform. And the reach of the platform can only be great if end users demand that platform and buys it. And they would only buy it if there are killer apps. So what comes first? The reach of a platform or a killer app? A killer app or a reach of a platform? Well, it turns out that these answers are very, very hard to solve, and that's one of the reasons why new computing models don't come along. Today, the CUDA GPU computing model has been established as a new computing model. It has delivered performance that is tremendously better than without. By accelerating the CPU, as I mentioned before, we're able to solve problems that otherwise are impossible to solve. We've delivered on CUDA year in and year out. We're now on our CUDA 9 generation. People realize that we're committed to this computing platform. The installed base of compatible computing platforms are now in the hundreds of millions. You could develop a CUDA application, and it will run literally everywhere. There are hundreds of applications now. Rich tools that make it easy to develop new applications. Amazing applications so that whether you're in any field of science, whether you're in molecular dynamics, medical imaging, energy discovery, material discovery, weather simulations, material simulations, mechanical simulations, the number of applications is incredibly rich. It doesn't matter what field of science you're in, we have applications that are accelerated by CUDA. And then lastly, the reach. Every single computer maker in the world, every single cloud computing platform in the world today has adopted NVIDIA CUDA GPUs. So it doesn't matter what country you're in, what industry you're in, or what field of work you're in. There is a computer your size, whether it's a laptop, a workstation, a server, a supercomputer, or a cloud service that runs all of these applications. For the first time, a new computing model has emerged. Well, our highest purpose ultimately is to enable developers and researchers to do groundbreaking work. And so it is incredibly rewarding when this year, the two Nobel Prize winners, the Nobel Prize winning of chemistry and the Nobel Prize for physics, were both helped by NVIDIA GPUs. Cryogenic electron microscopy, laser interferometer gravity wave observatory, one, an imaging system at the atomic scale, the other, an imaging system at the astronomic scale. For the first time, we're able to detect and recognize that gravity is a wave and confirm the prediction, the theory that Einstein made 100 years ago, that gravity is a wave. Two black holes collided millions and millions of light years away, and we were able to detect the little tiny chirp, the little tiny disturbance in the universe as a result of those two collisions. GPU computing made these computational instruments possible. We're so incredibly proud of that. Well, at the core of it, what starts it all is this massive industry, the largest high-performance computing industry the world has ever known. This industry is called computer graphics. Computer graphics is the simulation of reality. We have to make it physically real. We have to look real. And the simulation of photons, as you can imagine, is extraordinarily computationally intensive. On this wave, on this incredible computationally demanding and high volume market, we were able to harness the R&D scale that made the GPU possible. Well, the dream of all computer scientists and all computer graphics engineers has always been to create virtual reality, to create the holodeck. And so today, I want to show you our latest development in the NVIDIA holodeck, which is now available for early access. Let's take a look at the new NVIDIA holodeck. Hey guys.
Hey Jensen, how's it going?
You guys back there, Sean?
Hey, can you hear me?
Which one are you?
I'm right here in the middle, Jensen. This is Sean.
You're Sean, and who else is back there with you?
We have Kyle here.
This is Kyle.
And Roy.
This is Roy.
And so this is amazing. So imagine they're in virtual reality right now. Okay, we're not. We're in reality. They're in virtual reality right now, and they could be in three completely different places. It doesn't matter where they are. They could be in California, in Taiwan, somewhere in Kaohsiung. It doesn't matter. And if they were to design something and they want to enjoy it together experience it together, and do a design collaboration or design review together, they could go into virtual reality. Now, this virtual reality environment called HOLODECK has the ability to ingest, to take in, to import design files from any CAD tools over time. Okay, so whatever you design, you can import into HOLODECK. Whatever world you could create in HOLODECK. It's virtual reality. Everything in HOLODECK is physically accurate. It's physically accurate. The materials are measured physically. And so when we render the materials, it'll look like the materials. Carbon fiber will look like carbon fiber, and aluminum will look like aluminum. Car paint will look like car paint. Okay? And then the other thing is it obeys the laws of gravity. And so the laws of physics is obeyed. If you collide with something, it'll feel like you're colliding with it, so things don't go through each other. You could decide when you want to obey the laws of physics, and you could decide when you don't want to obey the laws of physics. You could pick up something really, really large if you desire. Okay? Everything is in virtual reality. But the most powerful thing about this environment is that they can be in completely different places. And what's amazing is that in a very short period of time, as they're standing there, you almost feel like you're in the same place. You're in the same world. Hey, Sean, why don't you show us what you can do in HOLODECK?
Sure. So first off, why don't we bring in a cool environment to check out some objects in? So we've created this lab environment so that we can explore lighting and detail in a realistic way. So let's bring in our car. Let's check this thing out. So this is a McLaren 720S. And using all of that CAD data, we're able to bring the entire aesthetic and design of the car together so designers and engineers can take a look at it together. The entire car is present, and using MDL, we've mathematically defined how light should interact with materials so that we can define what leather and carbon fiber and aluminum should look like. And using some tools in the HOLODECK, we can begin to make edits and changes and understand exactly how a design would come together. So this is our material selection tool, and using it, I can grab the car paint here and begin to change the parameters. We could change it to an entirely different material if we like to, but in this case, let's just check out some different colors.
Now, guys, remember, you're in virtual reality, so your frame rate is 90 frames per second. We're not in virtual reality, and so you just got to move your head slowly, okay?
You got it. So I like gray, but you know, everyone has their favorite color for a car.
How about right?
Hey, you're standing right into the selection board.
So we can choose any color that we really like and define our own, or even choose an entirely different type of material.
Okay, looks great.
We can
I
also
love
use
this color.
other types of tools in the HOLODECK to really get inside and explore the design. Hey Kyle, could you hand me the clipping tool?
Sure.
So using this cutting sphere, we can actually go inside of the geometry of the car. Let's do that again. So the clipping sphere lets us actually go inside, and we can go through the engine cover and check out the inside of the engine itself.
The entire original design database of the McLaren is inside the HOLODECK right now. This is not a video game, this is a real design.
So real designs, real products, and we can really explore the entire thing. We can also peel away the car layer by layer and get inside of the interiors of it entirely.
Wow, that's pretty amazing. What do you guys think? This is how we imagine design collaboration to be someday. And so the designers will design in their various tools, and they will import it into HOLODECK. And HOLODECK is a universal tool. It's a universal tool. It works with everybody's design tools. And so as a result, we can use this viewer, this HOLODECK viewer, to experience any design that you come up with. And we can collaborate, we can make changes to it, and we can, of course, accelerate the design of great products together. Anything else?
Well, that's it. Thanks, guys.
Hey, guys, do you guys speak Chinese?
Sure.
That's
我会
it?
讲 我会讲中文，
All right, you guys. 谢谢，拜拜。
谢谢。
再见。
So, HOLODECK. HOLODECK is a virtual reality laboratory. It has the ability to take design files, original design files, completely unchanged, as complex as you like it to be, and ingest it into this world. You can import it into this world. You can enjoy it together with different people from around the world. And all of us will be in the holodeck together. We'll see the product in its original fidelity, in its true fidelity, rendered with the actual materials and photorealistically, and everything behaves according to the laws of physics. But the most important thing, you can now enjoy virtual reality collaboration. We think this is really going to revolutionize the way that people do designs. Computer graphics, and by the way, early access is now. Okay, just go to the NVIDIA website and the holodeck section and request for an early access. Computer graphics was the first killer app of the GPU. The new killer app of CUDA GPUs is artificial intelligence. The buzz around AI, the energy around AI, as you know, is just absolutely incredible. The number of startups around the world that has been funded for AI has grown to almost $7 billion this year. 10x in the last 5 years. The number of papers, the research that's progressing all over the world, absolutely all over the world, has now reported 3,000 new papers this year. But this is just amazing. This is the Neural Information Processing Systems Conference called NIPS. It is the AI conference, if you will, Neural Network AI Conference. You could see that the trends for registration over the years has been rather normal. And all of a sudden this year, the registration is almost like a panic. Everybody registered instantaneously to make sure they can get a spot. In a lot of ways, NVIDIA GTC this year in Taiwan was sold out weeks before we opened door. And so I think that the interest around GPU computing, the interest around AI is really off the charts. AI has been able to solve some unsolvable problems. And these problems are problems that you simply can't write software for. And I'm going to demonstrate a few of them for you. These are examples where no one has been able to write software to do until now. And this software is written by the computer itself. In the first example, this is NVIDIA research. This is ray tracing. Ray tracing takes a long time. And each one of the photons, as it collides with a surface and ultimately bounces into our eyes, takes a long time to trace. Every single bounce is a lot of mathematics, and there are a whole lot of photons that are bouncing all over this world. And so when it's not complete, it looks like that, where the sparkles, the black dots, are where the photons hasn't reached our eyes yet. We've written an artificial intelligence network that takes this image right here and turns it into that image. And basically what it's doing is it's thinking about what would be the appropriate color. What is the best color that should go into that black dot? Okay, so take a look at that. It's happening so fast, it's not moving. You see that? It's rendering, and it's getting more and more and more and more clear. The second one is also done by NVIDIA research. This one here, by watching a video and listening to the words, we learn how to animate the face. It's the opposite of lip reading. Lip reading is you watch the animation of the face and you imagine what the words are. Here, you're listening to the words and imagining what the face animation should be. Okay? Okay, so watch this.
Listen up. The train yard warehouses is our main objective. Alexei, you and your men will do that. You have to go in and out very quick.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
So you now type in words, and we animate the face. This one, watching a video, the artificial network has learned the three-dimensional positioning of the character in three-dimensional space, 2D to three-dimensional inference, okay? So you're looking at a two-dimensional video, and it's going to transfer it to a three-dimensional space. And notice the shadows on the ground. It's in three-dimensional space. Okay? This is called pose estimation. Imagine the application for this. The application for this would be, for example, in the future, there will be a camera looking at me, and then in just a heartbeat, I would be inside the same holodeck environment as Sean. Does that make sense? This one's really cool. This is by University of Edinburgh. Oh, this is by a company in Canada called Wrench. They're really great guys. This is University of Edinburgh, and they taught an artificial intelligence agent how to animate themselves, how to walk. And you could put a different obstacle in front of that character, and that character will learn how to walk around it, over it, and how to navigate through it. Okay, watch this. It doesn't matter what the obstacles are, and it learns how to climb it. Comes up to the edge, doesn't like it. Look at it tiptoe across that little tiny bridge. Artificial intelligence. How do you write a program like that? How does a program like that happen? Well, artificial intelligence figured it out. This one's really cool. This is a robot that's designed by Peter Abil at UC Berkeley, and he's working at OpenAI. And basically what he's done is he went into virtual reality, and he taught using one-shot learning this robot how to recognize blocks, move blocks, stack blocks. Okay? Just a few examples. And then after that, the robot has to figure out how to do it by itself. Okay? So imitation learning with just a few examples. Incredible. These examples that I've shown you, are, if you will, when you think about it, they're kind of toy examples. They're all toy examples. But the beautiful thing about innovation is this. By recognizing the potential of a toy example in solving problems long term, you could connect dots and imagine the possibilities. None of these programs are writable by humans. How would any software programmer write the software? But yet we use this deep neural network model called deep learning. With a fair amount of data, we have basically allowed the software to learn how to create these skills. NVIDIA has become the AI platform for the industry. All of those breakthroughs that you saw earlier and the breakthroughs around the world are built on NVIDIA's AI platform. We support every single network, every single framework, irrespective of what industry or what type of network that it's optimized for. The number of innovations in AI is expanding all over the world. It's literally exploding. There are 2,000 startups that are working on NVIDIA's platform. They're in all kinds of industries, from healthcare to automotive, financial services, manufacturing, smart cities, keeping cities safe. And it's available on literally every single cloud, in every single data center, from every single computer maker. And today, we're incredibly proud to say that announce that we're partnering with MOST, the Ministry of Science and Technology in Taiwan. Minister Chen and I are going to announce today that we're going to collaborate to spread the knowledge of AI and the tools of AI throughout Taiwan. The industry revolutions that will be resulted as a result of AI is really unimaginable at the moment. We know that there are incredible amounts of energy that's dedicated to AI all over the world. And we want to make sure that we harness that opportunity here in Taiwan. And so we're working with MOST to spread the knowledge of AI. The first thing that we're going to do is to develop a supercomputer based on the NVIDIA DGX. The supercomputer will be one of the world's top 25, and it will be dedicated to doing AI. We're also going to teach 3,000 developers and engineers over the course of the next 4 years. 3,000 engineers through a program we call the DLI, the NVIDIA Deep Learning Institute. We're going to spread the knowledge of deep learning all over Taiwan. And we hope that as a result of that, new startups, new research, and new groundbreaking products will emerge. And as part of that, we'll bring the NVIDIA Inception program, which hosts and supports startups all over the world, the 2,000 startups I've already mentioned. We're going to bring that program to Taiwan for all of the startups in Taiwan. Okay? And so I want to thank Minister Chen for his partnership. Oh, where is he? Minister Chen. Ladies and gentlemen, Minister Chen. And for his visionary leadership and what he calls the Taiwan AI Grand Challenge. I think this is one of the most important initiatives that Taiwan has ever known. This is a very important time, and we're delighted to partner with you. Deep learning is not easy. Everything that I've said so far makes it sound easy. The results seem magical, but the computing stack is incredibly complicated. Remember, deep learning in the final analysis is a high-performance computing problem. And the high-performance computing problem that streams through terabytes and petabytes of data as it teaches this neural network. The software layer goes all the way to the fundamental computing architecture, the system software, distributed networks, middleware, libraries that accelerate linear algebra applications, and of course, optimization with all of the different frameworks. These are huge, huge scale problems, and there are so many different frameworks in the world. The number of layers of software necessary to be productive is actually quite daunting, and everything is moving. Everything's evolving, and everything's improving by a factor of 2, by a factor of 10 every single year. And so it's hard to even implement a deep learning stack. So what we've done is we've created this NVIDIA Docker, the world's first Docker that's GPU accelerated, fully CUDA accelerated. NV Docker will then containerize each and every one of these framework stacks. These framework stacks will have all of the optimization, all of the testing, and all of the latest releases of each and every one of the layers of software, all containerized. And it's all put up in the cloud. And that cloud is called the NVIDIA GPU Cloud. It's not where you do the computing, it's simply a registry for all of that software. A registry for all of the software, all contained in one simple place. All you have to do is go register and click and download that entire virtual machine of complicated containerized software will come down to your cloud or your data center or your workstation. Wherever there's an NVIDIA CUDA GPU, everything just works. And the beautiful thing is, because that container of software will run in a data center, in your workstation, or in the cloud, and in every cloud, it doesn't matter where you do your software development. When you're ready to develop your software or burst for a high level of training, it doesn't really matter where you do it, okay? Everything just works, and everything has been tuned. And so let me show you what it looks like. Ryan?
All right. I'm super excited to show this to you guys today because for the last year and a half, I've got to use this and take advantage of it. And I used to have to build frameworks by myself. I had to figure out which version of cuDNN, which version of CUDA, get the framework, spend a day compiling it. It was a lot of work. Now, guess what I think about? I think about what month it is. That's it. Today, it's October, 2017, October, so 1710. So let me show you. Let me log in. Here we go. So after you've signed up.
Now remember, Ryan's going to build the whole supercomputer. He's going to download all of the containers and all of the software stacks. Okay? All the operating systems, all the device driver layers, all the middleware, all the libraries, all the frameworks. He's going to build it.
It's absolutely magical. So now, to launch a job, so I want to launch a GPU or a deep learning job. So I'm just going to hit the create job button. The first thing I have to think about is where am I going to do it? So today I'm going to do it in the cloud. I'm going to do it on one of our nodes on Saturn V. So I click Next. And then I have to think, well, what am I training on? So today I'm just going to do a real quick example with MNIST. Because if it doesn't work on MNIST, it's not going to work. Okay? And next, I have to think about what container I'm going to use. And this is where, what month is it? So what I'm going to think about is, well, I want to use TensorFlow. So I can look through my list of containers that are optimized, and I find, there's TensorFlow right there. 1710, 2017, October. That's the latest version with the latest cuDNN, the latest CUDA, all optimized, ready to go. I'm going to click this one. And then I put in the command that I'm going to use to launch my job. And I'm ready to go. Next thing I have to do is give it a quick name. So I'm going to say, hello, MNIST. I'm going to launch my job. With that, I've not only got an optimized software stack, I've launched a job on a pool of resources that I didn't even have to worry about. I didn't have to worry about my friends logging into my node and hijacking my GPUs. This launched it on the back-end supercomputer of my choice, whether it's in the cloud, on my DGX station sitting right by my side, or on the DGX in my on-prem data center.
Now, Ryan, what's amazing is this. What you just did so far, what you have just done so far, is basically the capabilities of hyperscale data center companies. These large internet service companies who have large data centers and large IT teams and the ability to build these supercomputers. What he just did with that one button is what they do. They built the entire computer, got it all networked together, downloaded all the software, get it all optimized. That would take weeks and weeks and weeks and weeks and weeks. All of a sudden, with just one click, it's all been containerized. It doesn't matter what machine you want to run it on, whether it's an AWS or Microsoft Azure or Google Cloud or Tencent or Alibaba Yuan. It doesn't matter. It doesn't matter where it is. We're going to be all over the world, and you take this container and you select your ACE machine, your accelerated computing environment engine, and it downloads it, and boom, you're ready to go. Okay? Step number 2.
Step number 2, I want to see how my job is doing. This is where it gets really powerful, because before it was a lot more difficult. But now I can just dive in and look at my job as it's training live through the web interface. So here I already have telemetry of my job. So stats, this is my loss function as I'm training MNIST. Now MNIST on the VOLTA, that trains really fast, right? So it just dives down. But this is super powerful because I could be launching hundreds of jobs. And right there on my dashboard, I can see the progress of all of those jobs as they're training. So I can stop jobs that are kind of leveling out, or I can go in and tweak them.
Now, Ryan is showing something that's super simple here. It's called MNIST. Super, super simple. However, when most researchers developing their networks, at some point they're doing a hyperparameter sweep. They're basically going through just about every possible configuration of network to find the most optimum one. And oftentimes, they don't perform well. Because during your development, you want to see as soon as possible you're not performing well so that you can stop and go off to work on something else and try some other idea. This particular example does converge nicely, but you could just imagine the productivity to the developers to be able to run so quickly across so many different machines, all those hyperparameter sweeps, and to be able to visualize the effectiveness of that network so quickly.
Yeah, so do you want to see what it used to look like?
Yeah.
Let me show you.
Yeah, sure.
All right. So before, this is my terminal. I used to have to log in and execute a job. And so here, I'm just going to log the same job. Oh boy. Well, let's switch to Windows. Do that again. So this is actually really exciting. So here, I just launched a job. But now, let's say I want to iterate, like Jensen was saying, and I want to go in and kind of dial in my network. Maybe I'm debugging because I don't really know how it's going. Here, I'm going to jump into a container itself, and I can make modifications to my network. So let me just source.
And with this ability to work in the GUI as well as the command line, people who are just learning how to use deep learning could be productive right away, and people who are experts at deep learning can have all the controls that they want.
Exactly. So this is the power users. They can go in, they can make modifications to their network, and when they're ready, they can launch that job. So I'm going to launch the job as I normally would, and this is how I would normally look at the output. I would see the loss function as it drifts up on the screen, and I would say, how is it doing? But guess what? This is still on NGC, so it's connected to the cloud. So let me jump back and show you that job that I just connected to, like over the Pacific, just on the terminal, is running right here. And you can see that I've iterated several times on this job. I've been working hard on it. All of those spikes are different job launches because I've been just iterating.
That's cool. Okay, Ryan, thank you.
Absolutely.
Good job. We've taken the creation of a supercomputer and all of the software stacks on top of it, and we simplified it into this NVIDIA Docker container. All of these containers of software for every single version of the frameworks, and there are so many different ones of them, and there's all the different permutations and combinations of software layers that goes with them. Every one of them are optimized, are integrated, optimized, and tested, and will maintain it for as long as we shall live. And they all sit up in the cloud in this thing called NGC, the NVIDIA GPU Cloud Registry, and you can download it into any cloud, any data center, any computer with NVIDIA GPUs inside. We have democratized deep learning. We have basically leveled the playing field so that you don't have to be a hyperscale data center. You don't have to be a giant internet company. You can now have the ability to have the most modern deep learning stack wherever you are, whoever you are, and it's completely available to you, okay, maintained forever. All right, so that's the NVIDIA GPU Cloud. Did it happen?
Not yet. It's very soon.
Very soon. Let me tell you what I was going to announce. I can't tell you. All right. If it happens anytime in the near future, could somebody tell me?
Absolutely.
All right, this is one of those keynotes where the benefit of a cloud announcement is that when it happens, we're going to know. And so when it happens, whatever happens, whenever it happens, they're going to let me know. All right, so that's training. That's training. Deep learning has two phases. There's two phases to deep learning. The first phase is developing the network or developing the model. You have to support all kinds of different frameworks. It just depends on who you are, what company you work for, or what field of research that you're doing. You may decide to choose from one framework to another framework to develop with, whatever tool you decide to be more comfortable with. You develop the framework, the deep neural network. This network is a massive computational graph. It's a graph of arithmetic, and it has hundreds of millions of parameters. It's a massive file. It's a massive file with a really complicated graph. And what you need to do is take this massive computational graph and figure out a way to make it run on all of these devices, whether it's a hyperscale data center, a robot, or a little tiny thermostat. Okay? And these computational graphs come in all sizes and shapes. They could be, well, all sizes and shapes, and I'll talk about that. Inferencing is going to infuse intelligence into computers of all kinds. We already know that 20 million nodes of data centers in the future will all be doing inferencing. And the reason for that is because every single query that we make on billions and billions of cell phones every single day are going to pass through all kinds of neural networks. 20 million nodes in data centers all over the world. There are hundreds of millions of autonomous machines. Autonomous machines are machines that are able to perform their tasks intelligently and autonomously, even when it's not connected to the internet. And so the computing has to be done locally. And then others, trillions of devices are going to be connected to the internet. It could be a Fitbit, it could be a thermostat, it could be a video camera. There are all kinds of sensors all over the place that are going to be connected to the internet. And they're going to detect something and make an observation about the environment. Maybe it's a small vibration in an engine that detects that soon that particular machine may fail. Okay? And so these Internet of Things are going to be incredibly valuable, and it's basically going to be this massive sensor network that's going to blanket the Earth. And all of that information is going to go up into the cloud. There'll be supercomputers in the cloud trying to make sense of all that information. So inference will be run in all kinds of places. Inference, artificial intelligence inference, will likely be the single largest electronics market we've ever known. This is going to be the next computer revolution. Once you develop the network, you have to apply it. Once you develop the software, you have to run it. And running it, you run it on all these different platforms. There's going to be an explosion of inference devices. But notice, the sizes of them are so different. Everything from Alexa microphone to a robot to a self-driving car to a supercomputing center. The variety of networks is growing. There are all kinds of different networks you would develop. There are computer vision networks, CNNs. There are sequence networks, RNNs, recurrent neural networks. These revolutionary generative adversarial networks where you have two networks inside that network. One network is trained to detect the truth. The other one is generating new examples, trying to fool the other network. The two networks are competing against each other. One to detect the truth, the other one to fool the first one. As a result of this repetitive competition, eventually the network can generate all kinds of amazing things. This generative network could generate images, it could generate sounds, and they're going to be so realistic. GANs, and then reinforcement learning. Through trial and error, this network, if you gave it a value system, definition of goodness, every time it gets closer to goodness, it gets a reward. Every time it gets further away from goodness, it gets punished. And as a result, the reinforcement network tries over and over and over again. Eventually, it learns the task. All of these different networks are all exploding, and they're all evolving incredibly fast. Oh, by the way, there are 3 Easter eggs in here. There are 3 Easter eggs in here. Let me take it back off. There are 3 Easter eggs in here. Whoever can come find me later to tell me what those Easter eggs are, whoever is the first to come and find me, the 3 Easter eggs, all 3 has to be perfect, will receive a very special award. Okay? You want to see it one more time? Are you guys ready? Okay, one more time. Okay, there's 3 Easter eggs in here, all right? And whoever... It's a very expensive gift, so I cannot afford... If no one guesses it, it's okay. It's not mandatory. All right. So the number of devices where inference will be run is exploding. The architectures of inference of neural networks is exploding, and the complexity of neural networks is exploding. And the reason for that is because the effectiveness of the neural network is related to the computational capabilities of the networks. This little tiny dot here, this is AlexNet. This is the network that beat every single computer vision developer in the world in the year 2012. This little tiny dot of AlexNet has grown up, and the neural network, what I did was I took the number of operations per second and multiplied by the bandwidth, okay, just to give a measure, a feeling for the computational load. The CNNs has grown by a factor of 350 in 4 years. That's way faster than Moore's Law. Speech networks. The Deep Speech 1, this is Deep Speech 3, 30 times in just a few years. Natural language machine translation has increased also dramatically in just a few years. The complexity of networks is growing. So the architecture is changing. the complexity is exploding, and the number of devices we want to serve is also exploding. And that's one of the reasons why this market is so rich for innovation. It's hardly good enough, and we have years and years of opportunity to improve. Well, the answer is, how do we now take that computational neural network graph and compile it to all of these different devices? How do we take all of the outputs of these frameworks, run it through an optimizing compiler, and target all of these various devices? And so we created an optimizing compiler platform, an inference accelerating platform we call TensorRT. TensorRT 3, the third generation, is available today, and it's really quite remarkable. It's absolutely remarkable what it does. It basically tunes for the precision of the capability, computational precision of the target device. It takes this computational neural network and it removes all the unnecessary things, or it could fold a lot of computational layers, we call fusion. You could fold a lot of the computational layers, remove a lot of, and optimize for the memory hierarchies of your machine, and take advantage of the special instructions, make it possible for us to stream multiple streams of inferencing at the same time. Okay, so you can take very complicated networks and refactor it and refold it and re-optimize it, just like an optimizing compiler. So it has to take the output of all these different frameworks, recompile it, optimize it, and target it at the target device. Well, the results are really quite amazing. All right, so this is a CPU with TensorFlow output. This is a CPU with TensorFlow output. You can process 140 images per second. 140 images per second for a state-of-the-art CPU is actually fairly good. 140 images, it could detect what's inside those images, 140 images at a time. With our V100 with VOLTA's new instruction tensor core and TensorRT, we can process 5,700, a fair amount of speed up. Now notice, in the beginning I was mentioning, one of the most important values of a new computing platform is to give you a gigantic speed up or a gigantic performance boost in some metric that matters. And the metric that matters here in the data center is throughput. Okay? And for sentence translation, for natural language translation, from 4 to 550, 140 times speed up. Now this is what it looks like physically. If you were to build a data center, and today's the data center looks kind of like this. If you wanted to build a data center to be able to do the inferencing and support all the throughput of all those photos that are coming through, and you wanted to do, for example, 45,000 images per second, that's your target. It would take 160 CPU servers. And what's amazing is 65,000 watts, 65 kilowatts. Okay, 65 kilowatts in order to do 45,000 images per second. Basically about 1 watt per image. About 1 watt per image. This is what it looks like with TensorRT and V100. Let me show you again. Did you see that? 你看到吗? Save a lot of money. 以前, 现在. Yesterday, today. Very expensive. Save lots of money. Okay? And so one of the most powerful things about a computer revolution, of course, is saving money. Surprisingly, saving money expands the market. Remember, one of the most exciting things that's ever happened to Taiwan was when the computer became cheaper. It exploded the market. And I think the same thing will happen here. Artificial intelligence today is computationally very expensive, but we are soon going to make it very affordable. And by making it very affordable, we can save lots and lots of money, or more importantly, expand the market dramatically. The speed up, the reduction in power, the size is all completely discontinuous. And this is the benefit of NVIDIA's CUDA GPU accelerated computing. Let me show it to you. And so this is what I'm going to show you is this. Now, I don't know how many of you are experts at flowers, but there's, CC, do you know what this flower is? I have no, 你知道这个我看不出来，这是什么东西啊? No idea, right? None of us have any idea what these flowers are, okay? However, a computer program has learned how to recognize not only flowers, but what species of flower. Not only what flower, what species of flower. And so we're going to run this on a CPU. It's really a miracle. Okay, so this is the output of TensorFlow, and this is ResNet 152, I think. Okay, so ResNet 152 means 152-layer neural network. And now the CPU is running 4 images per second. 4 images per second. And through the miracles of deep learning, hey, Ryan, let's show them what the flowers are.
Yeah, let's take a look.
Through the miracles of deep learning, not only did it recognize that it's a flower, this is a grape, this is a primula. This is a Mexican aster. Have you ever been to Mexico? Wild pansy, osteospermum, passion flower, bolero lotus, that one I actually might know. Fritillary. The words fritillary has never left my mouth before until now. English marigold, purple coneflower, sword lily, primula, sunflower, okay. Good job.
We're getting better.
Wallflower, okay. And so this, ladies and gentlemen, this is CPUs doing inferencing at 5 frames per second. And this is the miracles of deep learning. Truly, truly amazing. Now let's take a look at it with V100 and TensorRT. A little bit faster, huh? You know what this looks like? This looks like money. Saving lots of money. Saving lots of money. So the more GPUs you buy, the more money you can save. Okay? Makes sense, right? Makes sense. That's why people are buying so many GPUs. They're saving money. Look at this. This is unbelievable. Okay. All right. Thank you very much, Ryan. Good job. Inference is the next major problem. Deep learning has two pieces to the puzzle. First is training. High-performance computing problem. The software stack is very complicated. The servers are very complicated. We created this software cloud registry that contains all of this complicated stack called NGC. Second, inferencing is high-throughput intensive. High-throughput intensive. Each one of these computational graphs has hundreds of millions of mathematical operations inside. And we want to be able to run it as fast as humanly possible. Because what happens is when you can run it fast, you could increase the throughput of your data center. As a result, you could reduce cost. Okay? And so, deep learning. VOLTA is the most complex processor the world's ever made. This is based on TSMC's 12-nanometer process, 12-nanometer FinFET. This is the largest chip humanity has ever created. This is the work of several thousand engineers for almost 4 years. Several $1 billion R&D budget. What I'm holding here, 250 amps of current goes through this one little tiny module. 3D packaging, TSMC's latest state-of-the-art CoWoS packaging, unbelievable complexity. This is the VOLTA V100. However, all of that, new tensor instructions, 21 billion transistors, new tensor core instructions, 120 teraflops, 120 teraflops, 120 teraflops. For example, a CPU is 120 teraflops, okay? 120 teraflops. And it's optimized for 2 applications fundamentally. One of them is high-performance computing, the discovery of new science, and the other one is artificial intelligence, deep learning. We created this architecture specifically for that. But I think that in the final analysis, what makes this launch so amazing is that it's now available literally in every single cloud, has been adopted by every single cloud, has been adopted by every single computer company in the world, from IBM to Cisco to Lenovo to HP and Dell. Every single data center in the world will have NVIDIA VOLTA. Every single cloud will have NVIDIA VOLTA. Okay? So the VOLTA is in full production. The momentum is incredible. Now, VOLTA is designed for several markets. And so now I'm going to talk a little bit about the market opportunity. The market opportunity, got several $1 billion in my pocket right now. The market opportunity for high-performance computing could be thought of in several segments. The first one is high-performance computing. This is the traditional scientific computing. 100% of supercomputers will have to be accelerated. Today, less than 10% are. 100% will have to be accelerated. And the reason for that is because simply Moore's law has come to a stall. And we need to continue to advance the amount of computation capability without escalating the amount of power and cost. And so there's no question in my mind that 100% of this will be accelerated. CSP training, cloud service providers, internal use of our processors for deep learning. I think it's very clear that almost every single application in the future will be an AI application. Inference, I just mentioned the 20 million servers that can now be accelerated so that they could either increase the amount of throughput or reduce the cost of their data center. Public cloud, this is the fastest growing segment of IT, already $25 billion today. The benefit that we offer is NVIDIA's CUDA is the standard of high-performance computing. It is the standard engine of big data analytics. And of course, high-performance cloud, one of their target customers is people who consume an enormous amount of storage, big data. Industries, whether it's whether it's healthcare, automotive, logistics, ride-hailing, manufacturing, high-performance computing will define the future of these industries. It is impossible to figure out which car should pick up which customer when there are so many customers and so many cars on the road. It is a large-scale high-performance computing planning problem. How to figure out which route to take so that these hundreds of millions of packages, which will be billions of packages per year, that has to be delivered to everybody's home, what's the best route? Saving a little bit of time, saving a little bit of fuel will make an enormous difference in a company's profitability. Healthcare, reading radiology images. So many different applications, self-driving cars. Industry after industry after industry, I think we're going to see artificial intelligence revolutionize it. And of course, the entire enterprise industry. Enterprise represents about $3 trillion overall, and we have several different products that we're working on for this particular market. One of them is virtualizing all of the computers and putting into the data center we call Grid and Quadro Virtual Workstation. And the other one is we're partnering with SAP, the world's leading ERP system, to accelerate their new platform called Leonardo, which is SAP AI. Okay, so this industry is going to be quite large. For each and every one of those markets, we have a computing platform that starts with the processor, the server, as well as the software stack. Building the chip alone is just the beginning. In the final analysis, each and every one of these industries, they value the software because they value productivity, they value results. And so in the case of high-performance computing, the revolutionary software architecture we call CUDA, the most pervasive high-performance computing architecture in the world, CUDA, is what made it possible for us to accelerate those applications. And then all of the SDKs and all the libraries and all the tools is all part of what's called ComputeWorks. For CSPs, we have the NVIDIA AI SDK. It consists of cuDNN, Nickel, which is a distributed deep learning collaboration system information routing system, incredibly complex, makes it possible for us to take a large job and spread it across a large number of nodes. TensorRT, I've already mentioned, digits, our UX and our environment for deep learning, and it runs on every single framework. And then lastly, public cloud, industries, and enterprise. We've got to make it nice and simple for everybody who don't have the benefits and the IT systems of these cloud service providers to be able to build their deep learning systems. We call it NGC. And we also virtualize all of the computers using Grid Virtual PC and Quadro Virtual Workstation. So this is our NVIDIA Tesla data center platform. But ultimately, to take it to market, we need amazing partners. And this is why Taiwan is so important to me. This is where the world's leading server makers are. Every one of the world's top server makers are based here in Taiwan. And I'm so pleased that all of them have partnered with us to take all of these GPU applications, engage these GPU applications in large markets all over the world with all of these different types of server products. Even though, as you know, GPU computing is one single architecture based on NVIDIA, everything runs on everything. CUDA is common across all of them. An application that's a weather simulation application will run on every single GPU, just at what level of performance and capability. But every single market and every single application has a different optimization point. And so if you're interested in deep learning, maybe 8 GPUs is the best approach. If you're interested in high-performance computing, maybe 4 GPUs is the best approach. And if you're interested in enterprise virtualization or transcoding or inferencing, maybe 2 GPUs is the right approach. We have configurations of all sizes and shapes. Foxconn, Quanta, Inventec, Wistron, Taiwan, Supermicro, Asus, Gigabyte. The world's leading server makers are all part of our Tesla platform. I can't be more delighted, and I want to thank you for your partnership and all for working with us to take this revolutionary computing platform to the world. Thank you. 100% of the world's $3 trillion industry served by these companies. Not bad. Let me give you a quick update on the next phase of AI. The first phase of AI is to infuse deep learning into all of the software and services that we have. It's going to make everything more intelligent and make everything apparently magical. Now, one of the projects that we're working on is self-driving cars. Without AI, this project simply would not be possible. But with AI, we can now realize, for the very first time, fully autonomous vehicles. Self-driving cars is going to revolutionize society in a way that few of us even appreciate at the moment. Not only are cars going to be more enjoyable to be in, it doesn't have to be about getting into your car to get to work. Getting to the car may be the enjoyment all by itself in the future. For many of you who have a busy life, you can appreciate what I mean. In the future, you might be, the happiest moment could be, I need to get in my car. Because it'll be quiet, you can spend some time reading, and it can naturally take you to work. Obviously, we'll reduce the cost of transportation. And as a result, the cost of goods will go down. As a result, the productivity of society will go up. The quality of life will go up. There's no question that urban environments will be redesigned. It's actually pretty exciting also to imagine how the car itself might be completely re-engineered. The idea of a self-driving car is even possible, and it's actually even so logical. This is a project that we're working on with Airbus. If you have autonomous capability, you can separate the wing from the car. The wing can come and pick up the car all by itself, autonomously. And so the car could be a very normal car. With electric vehicles, the battery pack and the drivetrain can be easily detached. And so as a result, what goes up in the air is actually fairly light. These type of capabilities make perfect sense as a result of two fundamental enabling technologies. So the last mile of transportation will be revolutionized by autonomous vehicles. Getting from your home to your destination will be revolutionized. And maybe even the 100-mile, the helicopter application will be revolutionized as a result of autonomous vehicles. Really exciting future. Well, this computing problem is actually fairly complicated. This is, in fact, the most complicated computing problem we've ever encountered. And the reason for that is this. We're taking sensor information from radars and LiDARs, inertial measuring units, and surround cameras of all kinds, and we're trying to perceive the environment in real time. We have to understand what we see. We have to figure out where we are. We have to reason about where everybody else will be, and then we have to take appropriate action, and we've got to do that instantaneously. And we've got to do that so well. We've got to do that so well that a driver and the passengers can actually go to sleep. What NVIDIA is doing is creating the whole stack. Our strategy is to create the fundamental computing platform, the processors inside, a new type of operating system that has the highest level of functional safety, all of the necessary computational middleware, and the applications on top that figures out what sensor fuses all the sensors, just as we fuse all of our sensors when we interact with the world, our ears, our eyes, the hair on our skin. Okay, we have a feeling for where we are based on sensor fusion. The car will also fuse all of its sensors, and using computational techniques in computer vision, parallel computing, and deep learning, we could figure out what's around us, reason about where we are, reason about where everybody else will be, and then take the appropriate actions. The additional complexity is, you know, that sometimes computers fail. Sometimes computers fail. And so this entire system has to be designed to the highest levels of auto grade, but the most complex part is that it has to fail operate. Meaning, even when it fails, it has to operate perfectly. I just said something that doesn't make any sense. Even when it fails, it has to operate perfectly. It's called fail operate. Okay, next time when I come back, I'll tell you how we did that. And could you imagine you're working on your PC, and all of a sudden the blue screen of something comes up, but it still keeps on working. Okay, and so imagine that. Very complicated problem. Well, I made a whole movie for you guys just to give you a sense of our current status. Guys? We're detecting all the cars. We're detecting all the pedestrians. It doesn't matter if it's snowing, raining, dark out. This is what the neural net sees. All the pedestrians. Surround perception. It doesn't matter the shape of the object as it comes around the car, we still detect it perfectly. Not only do we detect what we should not run over, we also detect what is free space, what's safe to drive through. We have to use different sensors to approach the same problem. Some of them we use cameras, some of them we use LiDARs. Where are we in the world? Using computation, we have to figure out what is the best path forward. Using artificial intelligence, we could also figure out what is the best path forward. Come to a stop, look at cross traffic. Make a hard left. Ladies and gentlemen, BB-8. So our strategy with driving is to build a computer, develop the entire system, operating system, the self-driving operating system, all of the middleware, basically the DirectX of self-driving cars, all of the applications, basically the Unreal Engine of self-driving cars, okay? All of the applications on top of it, put it into a car. We collect data all over the world. We train our network so that it could be drivable, and we test it all over the world. We have a fleet of cars. We built a data center so we could train the neural networks. We built a data center supercomputer so we could simulate all those miles. And then, of course, one of these days, if you could imagine, how would you do an OTA of a self-driving car? You have a brand new network. You have tens of millions of cars. How would you dare to do an OTA? You basically have to go back and re-experience the entire lifetime of all of those miles. And then when you're absolutely certain, you OTA the neural network into the fleet. Amazing undertaking. This is one of the greatest challenges of computing that I've ever known, and hopefully we can make a contribution. Self-driving cars is getting a lot of attention, but this in particular is really quite exciting, and the reason for that is ride-hailing, as you guys know, is very popular all over the world. Basically, on taxi, on mobile applications, and there's all kinds of people who are trying to revolutionize this space. It's predicted to be quite a large market. In just a few more years, it's going to be $1 trillion, $1 trillion market. It's very rare that you come up with $1 trillion market. And the reason for that is because we travel a lot. We travel a lot, and people are increasingly moving into urban areas. The number of projects that are all over the world, and all over, whether it's established car companies or computer companies, there are all kinds of different schemes and all kinds of different ideas on how this service could be brought to market. It's going to completely change the design of cars. I mean, this is just a beautiful car. You know, there's no engine, and there's no driver. And there's no driver, there's no steering wheel. If there's no steering wheel, you don't need somebody in front. You know, everybody's in front. And if there's nobody driving, of course, most of the time that you're in the car, you could be entertaining. And so this is quite an exciting opportunity. Now, the computational needs are just utterly staggering, and the reason for that is because this car is surrounded by sensors, and every sensor has redundancy. And the reason for that is because if something were to happen to this car, you can't tell the passengers to get out. You know, you got to finish the route. And so there's no failure available, and so acceptable. And so the number of sensor and computational requirements is quite high. This is what it looks like inside a self-driving robot taxi today. And all of these, all over the world, have multiple CPUs, multiple GPUs. There's several thousand watts. Now, just put it into perspective. Do you know what several thousand watts is? So suppose it's 3,000 watts, and the car's on the road for 10 hours. That's 30,000 watt hours. A battery is only 100 kilowatt hours, which means 3,000 watts consumed without the sensors. The LiDARs and the radars, they all consume power too. And not to mention, you got to move the car. Okay, so the computer alone consumes about 30% of the mileage or the range of the car, and that's obviously unacceptable. And so we've been working really, really hard on creating a revolutionary new computer targeted at robot taxi, and we call it Project Pegasus. And this is what it looks like. Project Pegasus has a whole bunch of sensors, and it connects to all the cameras and all the LiDARs and all the radars, and it basically takes a supercomputer and it shrinks it down into a few hundred watts. 500 watts total, 320 tera operations per second. 300 tera operations per second, basically several hundred servers, all shrunk into this one little tiny thing. A supercomputing data center in your trunk, the size of a license plate, and this is what it looks like now. Okay? So that's after. This is before. This is after. This is before several $billion of R&D, and this is after several $1 billion of R&D. And this Pegasus will be auto grade and will reach the highest levels of functional safety ASIL D. Okay, so ladies and gentlemen, Pegasus. I want to show you one more thing. The revolution of sensors all over the world, AI and now computers like Pegasus, those three fundamental ingredients, those three fundamental enabling technologies, sensors, artificial intelligence, and a computer that's high efficiency, that is designed for autonomous machines, when it comes together, it will start the next revolution. It's the second phase of the AI revolution. The second phase of the AI revolution is the autonomous machine revolution. We are going to be intermingled with all kinds of autonomous machines. In fact, I believe that everything that moves in the future will be autonomous. Everything that moves, every machine that moves in the future will be autonomous, it will have AI, and it will intermingle with us, move among us in a very natural way. The applications are huge. We know that robotics, manufacturing robots, building things faster, more complicated than any human could build, is going to be revolutionized. We know that we're buying a lot of things on the internet, and we want it to be instant. We know that you can buy a bowl of Neuro Mian, and it will show up in less than 20 minutes in Taiwan. But if everybody in Taipei were to be buying Neuro Mian, we're going to need a lot of these little machines to take it to you. Okay, Domino's Pizza, as you know, is already starting to prototype a delivery vehicle with NVIDIA's technology inside. The growing population of elders, as they get older, can have somebody take care of them during the day when nobody's around. Agriculture. You know the three greatest revolutions of humanity. First one is the automation of food. Agriculture. Food was produced by itself. Before agriculture, we used to chase our food. And then our food used to chase us. Right? And so agriculture made it possible for us to automatically grow food. The second was the Industrial Revolution. We automatically generated power. And we can send it to each other. Amazing thing. The third revolution is the automation of automation. Software writing software by itself. Automation of automation, otherwise known as artificial intelligence. This third revolution is going to revolutionize farming. The number of farming startups all over the world is incredible to increase the yield of the farms. 600,000 bridges, pipelines all over the world, buildings that are too tall to inspect. We can now have artificial intelligence drones that fly up and look at it to make sure that no small cracks or no small fissures are going to affect the integrity of that structure. Operations. In the future, it is very clear that most of us will be operated, if we ever have to be operated, by a robot. They can go into places we can't. They can make the perfect cut. Their hands never shake. They never lose concentration. Incredible. The robotics revolution. So we created a platform called Jetson. Jetson is a little tiny computer. It used to be, NVIDIA's products are very big. I would hold it like this. Now NVIDIA's products are very small. I have one here. This pocket is a supercomputer. This pocket is a baby supercomputer. Okay, this is the Jetson computer right here. This little Jetson Edge supercomputer runs CUDA, runs deep neural networks. Everything that comes out of TensorRT just runs perfectly. Okay? So you train the network on Tesla, you run the network on Jetson. And we named it after Jetson because of a cute robot. Jetson also has several very important elements. The Jetson SDK, computer vision algorithms, same problems that you have with self-driving cars. How do I perceive the environment? Where am I? How do I navigate? Digits, a deep learning system, and this is very important. This deep learning system also allows us to do transfer learning that I'm going to show you in just a second. And the third is a robotics simulator, the world's first photorealistic robotics simulator. I'm going to show you that in a second. And then lastly, Deep Learning Institute. Teach you how to apply all of this technology to build robots with Jetson. Okay? So these are the 5 elements of our autonomous machine platform. So how do you develop your own neural network? I just said it takes hundreds of thousands of very meticulously labeled images, millions and millions of test sets, supercomputers. How can everyone afford to develop neural networks? Well, you don't have to. What we've done is we've created a library in it's called a model library, model store, a neural network library in digits. That digits has a pre-trained library, has pre-trained libraries. Depending on your use case, that pre-trained library could be perfect or it may not be perfect. That pre-trained library has been trained to recognize things. It's basically like us. We know how to recognize things. However, when we look at the world from the top down, a 20-foot camera, the world looks a little bit different. And so maybe my detection rate is not as high. Maybe I use an indoor camera, my detection rate is not as high. Maybe I'm using a 360-degree camera, my detection is not as high. And so what I could do is this. I take my pre-trained network, download it from Digits. It's running on the DGX station or one of NVIDIA's servers. And you take your new data, which is all labeled carefully, and you retrain our network. You do transfer learning. You transfer your needs you transfer your knowledge into this network, transfer learning. This network becomes re-optimized, run it through TensorRT, run it through Jetson, and bam, just like that. 1, 2, 3. So easy. 好简单. Okay, so now the networks are wonderfully improved. And so whether you're using it for IVA or in surveillance cameras or one of my favorite applications, a police car in the future will have surround cameras. And you know they're looking for people. And they have license plates. And they have faces. They have cars. And they have a long list that's running all the time. A long list. And so they're just driving in the future. And they don't even have to pay attention anymore. They're just driving in the future. And the artificial intelligence network knows exactly what you got to look for. And it's just like the surround perception. You go bing, 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 and finds all the people. Okay? Pretty amazing, right? Okay? And so you could download our network. You could train it for that application. And it would just work. So Digits for adaptive transfer learning of our networks, pre-trained networks. The second thing I want to show you is this. Golf is hard. Golf is hard. Let's think about this. We want this robot to play golf. That is our mission. Okay? Let's break this problem down like engineers, shall we? First, I have to see the ball, see the environment. I have to sense my environment. I have to know where I am. I have to know where the flag and the cup is. Right? I have to perceive the environment. I have to sense where I am, relative to my destination. I have to understand the goals of this game. What is my goal? I've got to learn that. I've got to learn what is a putter. You got to pick up the putter. What is the way to hold a putter? What do you do with the ball? How do you read the green? So many complicated problems. If we were to break this problem down to write computer software, we would be writing computer software from the beginning of time until right now. It doesn't exist. Am I right? Right now, the world has no robot that knows how to putt. You put it in the middle of a golf course, it knows where it is. Hey, look at this. I know where I am. I know where's my flag. I pull the right club out of the bag. I go up to the ball. I hit the ball. I read the green, and the ball goes into the cup. Sounds so easy. It is 2017. Not one human has written this software. So we shall try. Okay? So we created this. Now, obviously, you cannot have Isaac do this in real life because while it's learning, it's going to break all the putters. It'll destroy the golf course, right? And not only that, it'll take forever. It'll take forever, okay? We cannot wait for Isaac to do that. And so we have to create a virtual world, and this virtual world has to look real. This has to look real. This virtual world has to obey the laws of physics. And this virtual world has to work at super real time so that Isaac can learn very, very quickly. And then when we succeed, we're going to take the brains of Isaac, this neural network, and we're going to put it into a robot just like this. And it should work. And that neural network will be able to control all of the joints and the motors of Isaac. The 20 some odd degrees of freedom. So many degrees of freedom. Okay, it's going to control all these things. Now, I cannot promise you that Isaac, the stroke is going to be as beautiful as Jack Nicklaus. But it will be very effective. All right? We only taught it effectiveness, not grace. All right, guys, Jeffrey, let's take a look at Isaac, shall we? This is Isaac. Hi, Isaac. Show us putting. So remember, Isaac has to see the world, know where it is, see the ball, pick up the putter. Okay? All right, but this looks very good. So let's see how Isaac started. Now, this is not even the very beginning. The very beginning is ridiculous. Basically, the very beginning, Isaac just standing there, doesn't know what to do. Shaking, just shaking. And through repeated shaking at very fast supercomputing rates, it figured out that its goal is to take this putter, hit the ball. Oh, that's a stroke. I'm sorry, that's a stroke. That's a stroke. We count every stroke. That's a stroke. I'm sorry, that's a stroke. We count every stroke. That's bad. Okay? That's a stroke. That's bad. All right? And so it tries and tries and tries and tries. That's stir frying. That's very bad. Okay, so it tries and tries. Let's move forward in time, Jeffrey. And let's show them the turf. Okay, so it's figured out. You see the grass, the green is, it has a slope. Okay, so Isaac's got to figure out through trial and error, basically infer the laws of physics. Does that make sense? Okay, so let's try. This is he's coming along. Okay, so let's go all the way to fully trained. Now Isaac is a master. Oh, nice. Nice. Huh? Boy, Isaac's going to take all the fun out of the golf for you guys. Okay, one more. No, I missed it completely. No. Oh, really? All right. All right, ladies and gentlemen, Isaac. Okay, thank you. It's very clear this is the beginning of a new time. Software development is going to be fundamentally changed. And software development using deep learning is going to enable us to solve problems that we've considered unsolvable before. Isaac is a perfect example of one. We would have considered Isaac to be an unsolvable problem. So complicated, we simply wouldn't even attempt it. There are so many classes of unsolvable problems that are now solvable. This software, deep learning, has made it possible for us to develop software, develop tools that are simply impossible in the past. NVIDIA is the AI platform. The NVIDIA AI platform has several components. It first starts with, of course, our GPU, our CUDA GPU. Our latest one is called VOLTA. It is now available in every single cloud. It's available in every single data center. But the software that makes VOLTA valuable is a complicated set of high-performance computing, supercomputing software stacks. And there's a whole bunch of them. There's ones for TensorFlow, there's ones for MXNet, there's ones for Caffe, there's ones for PyTorch, so on and so forth. And all of these software stacks needs to be able to run in clouds, in any cloud, and in any data center, any single workstation. Okay, we call that NGC, containerized all the software. Once you develop the software, the two-step process of deep learning is to then take that neural network, which is a complex, large computational graph, and compile it and optimize it for all the different targets. We call that TensorRT. As a result of TensorRT, the speed up of deep learning is so great that we can dramatically reduce the cost of deploying deep learning broadly in data centers all over the world. Today, it's simply too expensive. And so with TensorRT, we can finally do that. All of this is available in every single cloud. So the NVIDIA AI platform. We're so delighted to partner with Minister Chen to spread AI's infrastructure and capability all over Taiwan's industry. This is a very important time. In no time in my experience in history has there been a technology force as powerful as this that has the ability to revolutionize every industry we know. And so we're going to partner with the Minister of Science and Technology. We're going to build a powerful supercomputer here in Taiwan, and we're going to proliferate and teach through DLI deep learning skills all over the island. And it's part of the Minister Chen's AI grand plan. The next phase of AI, autonomous machines, where software leaves the computer and enters our world. And it can enter our world and perform tasks that we otherwise can't do ourselves. Jetson is our autonomous machine platform. The processor is a supercomputer that's designed to be very low in energy, very low in power, very high in energy efficiency. And along with it is all the software and simulation and infrastructure capabilities so that you can easily create autonomous machines. It's a really exciting time, and I want to thank all of you for coming to GTC. Let's go change the world together. Thank you very much.